So today we will see a different streaming algorithm about, so I will introduce first what is called frequency moments and then give an algorithm for counting distinct elements. And there's an idealized in bracket and it will mean something for us. Okay, so let's recap from the last time what we did. So again, so our streaming model will consist of objects coming in stream, and we have to store like some amount of information from this streamed object, which is the space is much smaller than the length of the stream, and we would like to compute some interesting function over the input. Okay. So last time we saw that we just all we wanted to do is count the number of distinct elements in a string. And for that, a trivial deterministic algorithm takes log n bits. And as we showed last time, that if we wanted to do something deterministically, we couldn't do anything better than theta log n bits. But if we allow both randomization and approximation, then we gave an algorithm which basically took essentially log n bits. And there were three basic steps that we followed in that algorithm. We first created a random variable x such that the expectation of x was exactly what we wanted to compute, right? And that is what we call unbiased estimator. But the unbiased estimator was a very good beginning point, but probability that it will give you what you wanted was not right. So then we introduced this trick of parallel repetition to reduce the variance. And basically our objective or the main goal is to show that whatever the numbers or the n tilde you want to compute, right, it is not too far away from the real number, right? So this is what we wanted to compute, right? So the n tilde which we want to return is within this range, and that is what this epsilon means. And delta is that probability that you are far away from this range is delta. Or in other words, you are within this range of n into 1 minus epsilon into n into 1 plus epsilon with probability at least 1 minus delta. So epsilon is called accuracy and delta is what is called confidence. Okay. And we saw that so what was the trick? So the trick was that if you take certain number of random variables, certain number of estimator, and took its average, it remained an estimator, unbiased estimator, but it reduced the variance. So you can actually achieve such kind of good epsilon delta approximation if you repeat 1 over epsilon square delta many times. Okay. But notice that there's a linear dependence on the failure probability. But what we would like to do is logarithmic. And then we introduced this median trick. So what we did in the median trick, if you recall correctly, is that let me see if you can add some pairs and let me explain to you, please. Okay. So what was our trick? Our trick was that, think of this. So we had this normal estimator, right? Normal unbiased estimator x, right? And then we made several copies of x, right? x1, x2, xh, whatever it was. And then our new random guy was 1 over h of summation xi. So this is our first step. Okay. And then we got this repetition step. Okay. And then we did something more fundamental. We said, okay, let's call this compound estimator, right? Why it is a compound estimator? Because it is taking an average of some H estimator. Now we took Z1, Z2, Z, say, capital delta, delta compound estimator, right? And from here, it gave us some number, say N1 tilde, N2 tilde, N delta tilde, and we sorted N1 tilde, N2 tilde, and N delta tilde, and returned median of this. Okay, and then what we were able to show that whatever we are returning from here, now to do this, what we did, we set up a random variable which said, well, we set up the random variable, say wi, which basically was a 0, 1 random variable, which said, are you far, like, there was, and we defined the notion of bad. What was a bad? So wi was 1 if it was a bad, and bad means you did not belong to the range 1 minus epsilon times n into 1 plus epsilon times n, right? If you did not belong to this range, then this was 1, okay? And then expectation of W was summation Wi, and what was an expectation of W? Because the way you choose second step, you can show that this is small or bounded, and hence now you can throw Chernoff and show that with delta being just log 1 over delta is good enough to guarantee epsilon delta approximation. Okay, so this is what we did last time. I will give you another example of this today, and we will see. So, but then how much space does this algorithm took, right? So we applied this median trick with delta being 1/3. So you apply parallel repetition to do the following thing. Okay, you get closer to accuracy, but the confidence probability is what is that called? Confidence probability is basically constant, right? So you succeed with a constant probability, and then you apply a median trick to boost the success probability to close to 1. Okay, now because the way I explained to you, so how much space, total space requirement was, right? So look, each of these guys at least remembers a number of size log n. So you need log n bits, right? And how many compound estimator we had? Log 1 over delta compound estimator we had. Okay, how many? What was h here? H here is roughly like 1 over epsilon square times delta. If you notice here, delta, but delta is some constant because we are applying delta with 3. So you basically apply 1 over epsilon square log 1 over delta log n. Okay, so this is the algorithm which we gave. Okay, so a natural question is in this setting is, can we do better? Okay, so let's do the following thought experiment. Okay, so what's the following thought experiment? And this is something which Morris itself suggested in its paper, is that why not be increment probability? Why we were doing 1 over 2 power x? Why not we do with probability 1 over alpha x for small alpha, then estimating n as 1 over alpha to the power x minus 1 divided by alpha. So you can show that this is also an unbiased estimator. Okay, so this is also an unbiased estimator. So there's no magical about 2. You could have chosen anything which is like 1 plus alpha, and you could have used your estimation as this, and you can do the same proof using induction as we did, and you can show that this is an unbiased estimator. But what is happening? So let's just go back and think. So if you increment, so look at the deterministic algorithm. I want to think that I'm incrementing that with probability 1.0 to the power x. So x, remember, what was x? X was the counter. X was the counter. And you were incrementing this counter with certain probability, right? Like, what do you mean by that? That at some point of time, you are incrementing this counter by 1 with probability 1 over 2 power x, and you are not incrementing this counter with probability 1 minus 1 by 2 power x. Okay, but now I want to increment this with probability 1 over 1 0. So whenever a new item comes, I increment this, right? Because whatever maybe that x is, this is 1. But it's a deterministic counter. It has a 0 variance, but it has a poor memory because remember, it takes log n space or log n bits. And when we incremented with probability 1 over 1 by 2 power x, variance increased, but memory decreased, right? So it seems that there is some sort of relation going on between these two. So this is why, like, why 2? Why not do 1 by 1 plus alpha to the power x? Then what happens that variance goes down and memory keeps increasing as alpha tends to 0. So there is some threshold which you can get and on the memory as well as on the space. Okay, so what one can get using this principle is the following. So if you set alpha equal to theta epsilon square delta, then it leads to 1 plus epsilon approximation with probability 1 minus delta. And what is your space now is log 1 over epsilon plus log n plus log 1 over delta. Okay? Okay. So you see, you can, by just setting this, you can also get dependence on epsilon to be log 1 over epsilon. But log n will not go because that is the size of the numbers which we are going to store. But other dependence can be made log over 1 over delta. And very recently, people have been able to get epsilon delta approximation in a space log 1 over epsilon plus log n, and the dependence on log 1 over delta is like log 1 over delta. So this is an unpublished work by Jelani Nelson. This is where I saw in his note, and someone else, I forgot his name. And what they are also able to show is that this is tight. So Morris algorithm, which was from 1980s or even older, it is still relevant, and only now people are able to get a correct space bound, both in terms of upper bound and lower bound. Okay, so any question on this before we move to the next set of questions? No question? Okay. So now I will move to next family of questions, which is about frequency moments. Okay. So anybody has a question? Okay, no, fine. So this is a fundamental class of problems, and it was formally introduced in the seminal paper of Alon, Matthias, and Zigedi, titled "The Space Complexity of Approximating the Frequency Moments" in 1999. Okay, and as I said before in my first streaming lecture, is that this is a paper which can be thought of as something which started this whole area of streaming algorithms. Okay, and so as always, so now here the settings will change slightly. Okay, so the setting is stream consists of E1 to En, where each EI is an integer in 1 to n, and we know n advance or an upper bound. Okay, for example, here n is 5 and the stream is like 4, 2, 4, 1, 1, 1, 4, 5, so on and so forth. Okay, so we know our domain. So for like this is very relevant. Very soon we will see where these kind of things occur naturally. But even for example, strings or characters or DNA mapping, we know that they are from very small range. But what is more important is that like they occur, same item or element occurs several times. Okay. Okay. And now, so given a stream, let fi denote the frequency of I or number of times I is in the stream. So for example, for here n equal to 5, what is our frequency here? What is f2? So f2 occurs 1. f4 occurs how many times? 1, 2, 3 times. f1 occurs, so maybe I should not have written like this, maybe doesn't matter. Let's see. f1, f2, f3, f4, f5. So f1 occurs 3 times, f2 occurs 1 time, f3 doesn't occur at all, f4 occurs 1, no, f4 occurs 2, f5 occurs 2. Okay, so this is what is called frequency movement. Okay, and based on this, you can get a vector, frequency vector f1 to fn. Okay, and what is the kth frequency moment? Is basically summation of fi to the power k, and whatever k greater than or equal to 0 you can think of. People also consider norms, and norm is nothing but you just take you compute frequency moment and take 1 by kth power of it. We will not worry about that, but I mean, we can do this. It's not big deal, but we will not worry about this. Okay, so I hope you have understood what frequency moments are. If you have any question until now, please ask. Okay, so now, so why is it interesting, right? I mean, sure, I mean, like this seems like some sort of generic number or generic objects, but why are they interesting? So there are some very important cases or regimes that it captures or that it considers. For example, what is k equal to 0? Right? Well, k equal to 0, what we know? K equal to 0, so any number a to the power 0 is 1, right? Right? And 0 to the power 0 is 0. So now what will it compute? So given a vector v, what is fk? So if you look at this, if fi is non-zero, it will become 1. If it is 0, it will become 0. So basically, f0 is simply the number of distinct elements in the string. Okay, great. And what is k equal to 1? f1 is that is basically the length of stream, because if you put k equal to 1, then you basically count. It's a just different way of counting the total number of elements in the stream. Like, okay, and for which we have already seen algorithm. It sounds very weird to count number of elements in this way, but nevertheless, this abstract model provides a framework to study all these things. Okay, and k equal to 2, f2 is a fundamental in many ways, we will see, and it finds applications in data sciences, machine learning, mathematics, everywhere, which is basically square of the sum of each of the frequencies. Okay, and there is another important case which is called f infinity, which is basically, if you put k equal to infinity, then this is basically you like to find an object with a maximum frequency. So among all this f1 to fn, which I has the maximum frequency? And this corresponds to something called heavy hitters problem, which we will see in next 2-3 weeks. And this is very, very important for data science, right? This heavy hitters problem, like which are the set of objects which occurs most frequently, right? And Uh, for example, so uh, yeah. So for example, in our example here, which is the heavy hitter, or so, oh, F5 is, this was wrong. F5 is 1. You can at least tell me that. So F1 is the most frequent element. But most frequent element also need not be unique. It could be several, right? Uh, but we will see how to deal with those. Okay. Okay. So the one where we want to compute maximum frequency is basically something called heavy hitters problem. Okay. There are also range between 0 and 1, and the range between 1 and 2. There is also range between 2 and infinity. They are mathematically very interesting, very challenging, and provides lots of tools. But it's not very easy relatable object. I mean, it's not something which I can relate it easily to something known. Okay, so that's a basic difference between these objects. But we will see an algorithm by Alon, Mattia, and Sisi, which will work for all the ranges. But for each of these special cases, like number of distinct elements, length of stream, which we already saw, this was Morris algorithm. Okay, we will see a specialized algorithm which does much better than a general algorithm about computing frequency moments. Okay. Any question?
Why 0 to the 0 to 0 is 0, not 1?
Oh, that's a mathematical I mean axiom. Don't ask me. It is actually 0 to the power 0 is considered 0. Yeah, I don't know, but 0 to the power 0 is 0. Okay. You have studied math, so I think axiomatically this is what it is assumed. I really don't know why it is this, but this is a convention. Let's say this is a convention. Okay, so I hope I have given you some reason to believe that frequency moments are interesting objects. They capture some interesting set of problems, and it's good to study them. Okay. So now, what kind of questions can we ask on frequency moments? So first question that we want to ask is that we would like to estimate Fk exactly, approximately, with small memory. So that's the one thing we would like to do. Okay. And second thing which is interesting is something called sampling. So given a stream nk, we want to sample an item I in proportion to fi to the power k. And now the question is, why do we want to do this? So in many of our applications, we want to find a random sample. Okay, so we want to find a random sample. Okay, but we do not want to find a random sample from the stream. Okay, but rather sample elements from the underlying universe, right? And how do we want to do? With proportion to its frequency in the stream, right? So this is why. So or with some power, okay? And we will see some of the applications of this. So you understand the difference between this? So look, you have a stream and you want to sample some elements from the stream. That's one question. Versus I would like to sample something from my universe from 1 to n, but from this particular stream, I want to sample with respect to the object which occurs with respect to its frequency, right? So this differs. Otherwise, if you notice that for all m size sample, things will look very similar. But here, now, think of like this is like a weighted sampling where weight depends on the stream itself. Okay. So this is another question which we like to do. And another question which is important is, given a stream K, can we create a sketch summary of small size? Okay. So what I mean by this? So what I mean by this is, like, we would like to take the stream and store a compact data structure, okay, of the stream, so that we can use this sketch or summary along with summary or sketch of other stream, so that we can get a sketch or summary of a concatenated string. So think of this, that you have a stream 1, stream 2, stream 3. So you keep small sketch of this, small sketch of this, small sketch of this. And when I say sketch, given this, you would like to be able to decode the information you wish to decode by looking at this. Okay. And now you would like to concatenate these things and say, oh, hey, look, I have, and this is very useful in while when we do lower bounds and things like that. So for each of this stream, I have a small sketch or small compact data structure. For this small compact data structure, small. Now we'll just concatenate this, or we'll take this, and then we'll prove that generally that this is a sketch of the concatenated string. Okay. So that we can get a sketch or summary of the entire concatenated stream. So naturally, if you notice, streaming is more difficult than sampling, and sampling is more difficult than estimation. Okay. But notice, all these questions are very easy if we do not care about memory, right? Because basically what we can do, as I told you, right, we know, so we know that we know the range, right, from where the items are coming, right? So you basically can store an array 1, 2, 3, n. You can store array, and whenever some number comes, you just increment it by +1. So if I comes, you increment the ith location with +1. So now at the end of the stream, you have f1, f2, fn, right? How much space it will take? How much space it will take? Anybody? What? Yeah, so it will take n log m bits. So this is, it can take n log m bits. Okay. Okay. So it can take as much as n log m bits. So we can, but this is only interesting when memory is much smaller than n. Ideally, we would like to do in polylog n memory for some fixed c greater than or equal to 1. And note that you can easily prove that log n is kind of lower bound, because log n is roughly the memory required to store one token or one number. I mean, you need at least this much, right? So in some sense, log n provides a lower bound, and we would like to do come up with an algorithm which is able to do these things in polylog n time, okay, or polylog n space, okay. So as I said, it takes n log m bits. You can also do, there are, like, if you notice here, there are lots of spaces which are vacant actually. Right? Maybe they are vacant, right? So you could also kind of go on creating, whenever a new item comes, you create space, right? So you can actually reduce a little bit and make it, I would say, output sensitive, right? So if you have a k elements, you can probably do it in, we'll see, in a k log m bits. Okay, we'll see some such things. Okay, and for most of these interesting problems, like for example, omega n lower bound on memory, if one wants to exact answer or wants deterministic algorithm. Okay, okay, or deterministic. I think what I meant here is deterministic approximation algorithm. Okay, so for example, even to count f1 or f0, okay, we need omega n lower bound if you want an exact answer or you want deterministic answer. Okay, and we'll prove, I mean, if not prove, at least I'll provide you some uh, like this is, and these are unconditional lower bound. They are not conditional lower bound. These are unconditional lower bounds. Meaning, basically, these will follow from applying pigeonhole principle appropriately. Okay. Okay. So, so hence we focus on 1 plus epsilon approximation algorithm or a constant factor approximation algorithm and randomized algorithm. So you can show that you cannot even have a constant factor deterministic approximation algorithm without taking some omega n space. So like in some sense, if you are really want to be in the regime of 1 plus epsilon minus approximation or constant factor approximation, then you have to come up with you have to take a randomized algorithm. So these are some places where notice that generally randomized algorithm and deterministic algorithms are, like in terms of normal, if you talk about time, they are not too different in some senses. But if we talk about space, then these two things start to behave very, very differently. Okay. Okay. So any question? Okay. Okay. So if there are no questions, then let me go forward. Okay. Okay. 1 second. Okay. Okay. So there's also a notion of two kinds of notion of approximation. One is relative approximation. So I'm sure this sounds a bit ugly, but basically all it is telling you is that suppose you have a real valued output of a randomized streaming algorithm on a stream row. We say that A provides alpha beta relative approximation for real valued function G. If basically just multiply with 0 every. So it says probability that A row output of your algorithm minus, and G is a non-negative function, okay? G row, whatever you wanted to compute, okay, is greater than alpha times G row with probability at most beta. So this is all that it is saying. I mean, I have just divided by 0, okay? So these are called relative approximation. There is also an absolute approximation or called additive approximation. And this is useful when you have G row can be negative, then we focus on this additive approximation. So basically here it says, okay, how far away from your real quantity you are, it should be at most beta. So I mean, you can read the definition in the slides. You will see it's like in action soon. So let's not waste our time on the definition. Okay. So, so what I want to do, I want to estimate distinct elements. So basically now we want to compute F0. Okay. So do you remember that? It's like, so basically we have streams, E1, E2, blah, 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 right? So like, or say for example, just for example, 1, 2, 2, 3, 4, 4, 1, 2, 1, 2, 3, 4, dot, dot, dot. And we want to know how many distinct elements are there. One is repeated several times. So basically there are like 4 distinct elements. Okay. So this is what. So, so this is what we would like to output. So why, so as I told you, right? I mean, why these things are interesting or why people care about them. So suppose you're given a stream row and you want to know how many elements did we see. So for example, you have a network switches, okay? You have a network switch, okay? And you know that lots of packets goes, right? And you'd like to know in a particular window how many different IP addresses you have seen. Do you know how many bits IP addresses are? Anybody? Many of you are much more practical than me. Do you know? So actually there are different IP models, but you could have as many as 128 bits. So the different addresses, the IP addresses the packets could have is like, so it could be a number between 2 to the power 128. So any address between 2 to the power 128. But within a window, you don't expect to see all these numbers, right? Or all these IP addresses, right? So it is important, but you want to know how many distinct IP addresses has passed through this particular network switch or something. And that is where you like to compute or get an estimate on the number of different, what you call IP addresses, right? Or some estimate. And look, you have to imagine that the kind of setting we are, N is also in some sense will be large, and M, the stream, is also very large. Okay. So why did I say this? Because what could be a trivial solution for this problem, right? What could be a trivial solution for this problem? So one solution could be is that I keep an array, right? How many bits it will take? Anybody? So you have 1 to n. Look, at least some of you should also speak. I mean, not all the time I should be speaking, you know. I feel lonely in the world then. Okay. So this is a simple, if someone else would like to tell a solution, then please go ahead and tell me.
It's your previous solution that every time you see it, you increase the count by 1.
But previous time we were counting frequency. So we took n log m bits. Do we need that much now?
No, you just need n because you need 0 and 1 basically.
Exactly. So like if you already have seen some element, then you don't increment it. So just at least in this trivial solution, we can avoid this. No, the reason why I said this, because I will give you a proof eventually that, I mean, you cannot do with n minus 1 bits. right? So it is important to understand that, yes, we can do with n bits. You get my point? Okay. So we will see that omega n bits are necessary. Can we come up with any other solution?
So how much probability do you want to succeed?
Oh, I'm not talking about probability at all at this point of time. Some offline solution.
Just keep only the distinct elements?
Yes, we can just keep the distinct elements, right? Right. We can just keep the distinct elements. Okay, that's great. Just keep the distinct element. Right? And that will take k log n bits, right? So here, but how will you go about doing whatever Venkatesh just now said? Is as follows. We can keep some dictionary data structure, right? So for example, here is my distinct element offline solution. So I initialize some dictionary D to be empty. And while stream is not empty, let E be the, look, I'm not caring about the time at this point of time. Let E be the next item in the stream. If E is not in the dictionary, then you insert E into the dictionary, increase K to K plus 1, and you output K, right? And this is going to take, so to do this, what kind of data structure can you use? So this is the algorithm which we are going to do. So we are going to keep a dictionary, and whenever an element is not there, we're just going to put it inside. And one thing is we can keep binary search tree, and this space will be like order K. I'm like, it should be K log n bits, so say order K words, okay? But the total time will be like M log K, right? Because each time you have to search whether these elements exist or not, right? We can also do hashing, which will take space order K, but expected time will be like order M, right? So these are two offline solutions which you can. So these are like, these are also what is called output sensitive solution. Okay. So, right. So an expected time to, to build this is like order M time, right? Because, yeah. So what I would like to do is take the second idea and take it forward. Okay. So suppose this is what I would like to do. I want to use a hash function from n to some capital N, where n is some polynomial in n, and store only the minimum hash value C, right? So how many bits do we need then? So what I'm going to store? I'm just going to store one number, okay? I'm just going to store one number, right? So at any point of time, an item come, okay, or element come, I look at h of E, okay, and suppose this is my x, I check if x is less than, if x is greater than equal to h of E, or rather, if x is greater than h of E, replace x with h of E, else. That's it, else keep x, right? So I'm just going to keep one number, and within this range, 1 to this thing. So since n is like some n to the power C, ordered log n bits are enough for us to keep this. So is the algorithm clear? I mean, why this will work or not, we'll get there, and it will take us like at least 2 more lectures before we get there, that why it works. But just for the sake, what are we going to do? We are going to keep a hash function, which when the number will come, it will map to some 1 to n, and just keep the minimum. And at the end, it will say, hey, it will output a function of, so at the end, my algorithm is going to output some function of min ei hei, okay, or some f of x. which is our minimum. So this is what I'm going to return and say, look, this is the number of distinct element, okay, based on whatever number I have stored. Now, why is this good? So now, to understand why is this good, we are going to get away from this. We'll come to this much later now. We're going to assume an idealized hash function, and that is fully random over the real interval. What I mean by this? First of all, it is a hash function. So forget about hash, it's a function. What is the meaning of function? So first of all, h is given by something, okay? So h takes value over 0, 1, this continuous interval, like uniformly at random. So any number you tell me between 0 and 1, which is uncountably many or uncountable, okay, it takes one of these numbers uniformly at random, okay? Okay, so this is what it is going to do. And for each element, so for each number, so for each h of I is a number in 0 to 1 uniformly at random. So this is what this idealized hash function is, okay? Okay, fully random. Now, suppose there are k distinct elements in the stream. So then what happens this? Then let's try to understand what happens. So suppose we had 1, 1, 1, 2, 2, 3, 4, 5, 6, 7, 1, 1, 2, right? What will this hash function do? It's a function. So this is going to map all these 1. Suppose this is 1 to some number between 0 and 1 uniformly at random. Like any of the number between 0 to 1, it can take uniformly at random. So basically it has collapsed all the 1s to one number between 0 and 1. All the 2s will go to some number between 0 to 1, okay? All the number 3 will go to somewhere, 4 will go to somewhere, 5 will go to 6, 7. So whatever may be the stream size, right? My hash function is going to give me k numbers between interval 0 to 1, which are uniformly at random, okay? Okay. So before we go, let me ask you a following question, okay? Suppose okay, now let me ask, what is the expected value of the minimum of hash values, right? So this is what my algorithm does, right? It does this, it applies this idealized hash function, okay? And so what does this idealized hash function does? It just maps a number between 0 and 1, interval 0 and 1, uniformly at random. So all the 1 has been mapped to. So if I look at my interval here, my algorithm has mapped to somewhere here, like some k guys, k values. Now the question is, what is an expected value of the minimum of hash values? Okay. So just to make your, okay, suppose k equal to 1. Okay. What do you think the value will be?
1/2.
Exactly. So what does it does? It actually divides the interval into 2 equal parts. Am I right? So what should I return? How many distinct elements? At least if you k equal to would have been 1, then number of distinct parts minus 1, right? So 1 over minimum, right, minus 1. Okay, so this is just to give you an intuition. Now what we can prove is a very, very strong theorem. Okay, so what it tells us, suppose x1 to x2 xk are random variables that are independent and uniformly distributed in 0 1. Okay, and let y is minimum of this, then expected value of y is 1 over k plus 1. So what it tells us is basically, so as William said just now, that if you take an interval 0 1, okay, and k would have been 1, then you expect it to be half. Say k would have been 3. Okay, then actually what happens is that this lemma tells us that, well, then you divide 1, 2, 3 equally 4 parts. So it's like 1/4, half, 3/4, right? So you just take minimum of all this, okay, and you just subtract 1. So if you had k guys, right, if you had k guys 1, so you would have been divided into equally 1 over k plus 1, 2 over k plus 1, so on and so forth. Okay, but look, this is probability, right? And so, I mean, it's not something which happens this way. So we have to prove this lemma in an ideal way. Okay, so let's see. I wrote down the proof. So let me. Okay, so let's try to compute the expectation of EY. So to do this, let's ask ourselves, okay, here is your 0 1 interval. Okay, now suppose y is infinitesimally between, say, t plus dt. This is y here. Okay, now we would like to, we would like to compute the density function of y. So basically we would like to compute what is the probability that y belongs to t comma t plus dt. Okay, so this is what I'm interested in. So I want to say that the minimum is going to be in the interval here. So this is the interval where the minimum is going to belong. Now I really don't know. I mean, either x1 could be a minimum, or x2 could be a minimum, or xk could be a minimum, right? So one of these guys could be minimum. Okay, so let's guess one of them. Okay, so suppose xi is the minimum. How many choices do we have? We have k choose 1 choices. Okay, great. Now, what do I know? If xi has to be, or say for example, x1 is the, if x1 is the minimum, then x2, x3, xk must belong to the interval where t plus dt, comma 1. Am I right? It must belong to this interval. Okay, and these are independent. So x2 also belongs to this, x3 also. But what is dt? dt is infinitely small. Infinitely small, or infinitely small, whatever. So rather than saying this, we can just say that this belongs to t comma 1. So basically, what is the probability of this? Well, y x1 to xk, any one of them could be y. So this is k choose 1. And given that I have chosen that, x1 must fall within this range t plus dt. So that is your dt. Okay. And everyone else must fall. Everyone here must fall here, this range, which means I have 1 minus t. And how many of such objects are there? K minus 1. So this is your probability. Okay? But now what are we interested in? We are interested in computing expectation of y. Well, I mean, this dt, there was nothing here. It could be here, it could be here, it could be here, it could be here, it could be here. So basically, expectation of y is 0 to 1 t times k choose 1 1 minus t k minus 1 dt. Okay. Now let's substitute 1 minus t equal to z. Then you will get 0 to 1. K anyway comes out. T will become 1 minus z. And this will become z power k minus 1 dt. Okay. Am I right? Sorry, dz. Is this correct? I substituted 1 minus t equal to z, or there is some minus missing. I think there should be z minus 1, right?
There is a minus because dt
Is
is
minus
minus
dz. So I shouldn't write 1 minus z. This should be z minus 1, right? This should be z minus 1, right? Right. Now, if you do integration by part, which I'm not going to do, if you do integration by part, okay, you will get 1 over k plus 1. Okay, so this completes the proof. Okay, so what did we learn? We learned that this lemma provides us a very nice what is that called? Unbiased estimator, right? And once we have this unbiased estimator, our algorithm is very simple. What does our algorithm does? Here. Assume that you have an ideal hash function from n to 0, 1. You initialize y to be 1. While string is not empty, what you do, let e be the next item in the stream, okay? And y is minimum of z comma h of e, right? And you output 1 by y minus 1. So if there is no element, then you will output 0, and otherwise you will output everything else, right? So this is our basic estimator. So this is our basic estimator, right? Now, this is not good. This is a first starting point. So remember, for Morris algorithm, we also had this basic estimator, and then we computed it. But we want to get an epsilon delta approximation. We want to say, hey, probability that like we are really returning number which is close to what actually is close. It's like 1 minus or 1 plus epsilon approximation, and we are returning this with very high probability. So we want epsilon delta, where epsilon is accuracy and delta is confidence, right? So we want epsilon delta approximation algorithm for this problem, okay? So now to do that, first thing we will do is compute its variance, okay? Okay. Okay, so this we did, okay? so to compute its variance, right, of y, I will show this. Okay. So how can you compute variance? So I want to compute expectation of y square. What is y square? Let's look at this. Okay. Can anybody tell me what will be expectation of y square? Look, we know the distribution, we know the density function of probability of y belonging to t comma t plus tt. This we know, right? We showed this is equal to k choose 1, or k, I should not write k choose, right? And 1 minus t, k minus 1 dt, right? Now, what is y square? Y square is a random variable which takes value between 0 to 1. Suppose y takes a, y square takes a square. That's all that it does. And what is the probability that y square takes a square is same as what probability y takes a. So expectation of y square is very simple. So expectation of y square is essentially, we can compute at base, so expectation of y squared is t squared k, choose 1, which is k, 1 minus t k minus 1 dt 0 1. So this integration. Okay, you again you can do substitution, and substitution z equal to 1 minus t, you will get k 0 to 1 t squared, yes, t squared, correct? No, you will get z minus 1 whole square zk minus 1 dt. Again you apply again integration by parts. Okay, not going to do. Okay, I mean this you should do. I mean, it's not something which is very difficult, but you get exactly this number which is like k over 2 over k plus 1 times k plus 2. Okay, so this is what you get, right? So this is what you can get expectation of y square. But if you have an expectation of y square, what is the variance of y? Is basically expectation of y square minus expectation of y whole square, right? So I mean, then we can just compute right here, 2k plus 1, k plus 2, minus 1 over k plus 1, okay, whole square, right? And this is nothing but, I mean, if you do some more computation, you can show this is less than or equal to 1 plus k plus 1 whole square. Okay, any question? Okay, so this is how we can compute its variance. Okay, I'm like, okay, so this is, yeah, so you will get this k by, so if you, I mean, I did not do this, but I mean, yeah, so let's go here. Okay, so if you subtract that minus this, you will get this, and k plus 2, k by k plus 2 is less than or equal to 1, so this is 1 over k plus 1 whole square. Okay, so this is the variance we have computed. Okay, okay, so variance is 1 by k plus 1 whole square, and k is something which depends on the number of distinct entries. So it could be as bad as n, right? Now, assuming that we have an idealized hash function, What did we do for Morris algorithm? We took average of H parallel and independent estimates to reduce variance. That's the first thing we did. Then we applied Chebyshev to show that the average estimator is a 1 plus epsilon approximation with constant probability. And then we use preceding and a median trick with order log 1 by delta parallel copies to obtain 1 plus epsilon approximation with probability 1 minus delta, right? So this is what we did for Morris algorithm. So now we have got a very nice estimator. And so if you notice, if you take H parallel independent estimators, then how much you variance reduce? You reduce variance by 1 over H. This is what you do actually. This is what you, why? Because if you recall, variance of AX is nothing but 1 over A square X, sorry, variance of X, and variance of summation Xi. If Xi were independent, then this is nothing but summation of variance of Xi, and we're like, so this is nothing. So whatever maybe it was, like, so whatever, so this is like now, so if you do here, so here you're going to return variance of Xi by H. So this becomes 1 over H square, variance of Xi. So whatever maybe the variance of X is, like, because they are parallel copies, so it is 1 over H square times H of variance of X, which is like variance of X by H, right? So if you had a normal estimator and it had some variance, then by making H copies, you reduce its variance by factor H. Okay, so this is an usual trick. This is nothing. This is nothing about this problem or that problem. Like, it's a problem independent thing. Okay, so let's just try this. So we will run the basic estimator independently in parallel, and we computed x1, x2, xh, and then when z is basically an average of this. So why? So first of all, as you said, right, you have to prove that expectation of z is what we want. So what is expectation of z is 1 over h summation I equal to 1 to h expectation of xi, right, which is 1 over h k plus 1 h times k plus 1 h 1 over k plus 1. So this is a good, this is an unbiased estimator as before, right? So because of this expectation property and this, whenever you take just normal average, if you started with an unbiased estimator, it will remain an unbiased estimator. If you started with an estimator which is approximately close to the number you are counting, it will remain that way. So these tricks are, and then you output 1 over z minus 1, okay, as before. So this is nice. Now, what is an expectation of z? Is 1 over k plus 1, because it is the same I just now showed to you. And what is a variance? Because of our general trick, right? If variance of ax is 1 over a square, variance of x, blah, 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 1 over h square, blah, 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 variance of x divided by h. So we computed variance of h to be 1 over k plus 1 square. So if we take h copies, the variance decreases by factor 1 over h. So we got 1 over h. Great. Now, suppose I set h equal to 1 over eta epsilon square. So if you recall the definition of Chebyshev, what was the definition of Chebyshev inequality? So the Chebyshev said, let me see. Okay, so here it is. So what did Chebyshev said? Probability x minus mu is greater than or equal to a is less than or equal to variance of x divided by a square. So what is our variance of x? Is 1 over h 1 over k plus 1 whole square. And I want, what is my a? Is epsilon by k plus 1, right? So this will become k plus 1 whole square divided by epsilon. So this gets cancelled, 1 over h epsilon. And what is h I'm picking? H which I'm picking is 1 over, so this is like 1 over eta epsilon square I think I made a mistake somewhere. Yes, because this should be epsilon square. So this will get cancelled, and what you will get is eta, right? So by a direct application of Chebyshev, you are able to show that you can get an epsilon and eta approximation, right? So what is my accuracy parameter? Epsilon and eta, but number of estimator we have used is h is like 1 over eta epsilon square. But look, this is for z, right? This is for z, but what you need is for your estimator is 1 by z minus 1. So you can also show that with probability that 1 by z minus 1 minus k is greater than. Okay, so this is, sorry, this is an error. It should be here. This should not be here. Okay, is less than equal to eta. So just by previous argument, you can just show that the estimator is good, like this. Now, as I told you, right, this eta is in your hand, right? Eta is in your hand, right? So you do not want the dependence of eta to be like linearly, okay? So now we can apply our median trick, okay? So what we will do, so you basically repeat log order n 1 delta times and you output median. So what we do, what we generally do, so we will take compound estimator z1, z2, z, say delta, okay, and then compute these numbers, say n1 tilde, n2 tilde, n delta tilde, and then sort them, return median, okay, right? And then as for Morris algorithm, we can apply, I will not go into, I will put this into the lecture notes, but I will not go here. And you output the median of these things, and then you can show that error probability is delta, and all you need is just log 1 over delta times, see, the base is order eta. So if you do computation, base is order eta. So this is why we apply this algorithm with a constant probability, like something like 1/3 or something, then this becomes some constant. So your overall dependence total, so how much total amount of space this algorithm took? Okay, how much? Well, we were assuming that we have independent random, like random hash functions, right? Which are uniform in 0, 1. They don't, I mean, well, to represent a real number, I mean, you require a lot of precision. So we will not get there. But let's say how many numbers will be stored. So the total number of numbers we will store is basically order 1 over epsilon square log 1 over delta. Of course, there will be some constancy, but forget it. Times whatever that real number that we wish to compute. Okay, but this is just to give you an idea why this minimum object works. Okay, but do we have an idealized hash functions? Okay, so in practice, what people actually do is that they take n to be large, and then they pretend that they have embedded this n into this 0, 1, and they work, and it works quite very well in practice. Okay, so this is an algorithm from 85, and this still works in practice. So you can simulate idealized hash function in practice by just taking n large enough and mapping them somehow to 0, 1. Like say n is like n cube, then you basically map to 1, 1 by n cube, 2 by n cube, so on. So you basically make finer and finer partition, and it works well in practice. But it's a course in theory, so we need to make an algorithm which is with regular hash function, not with this idealized hash function. Hash functions which can be stored in a small space, and computation which can be done in small memory and efficiently. Okay, so and several variants of these ideas with different trade-offs between memory, time to process each new element, and blah and blah. So now I will take a break for 5-10 minutes, and then after that, after the break, we will come back to this new algorithm about computing distinct elements in a real way. But for now, we will completely take a break and learn how to make hash functions, because they will be a useful object for our the whole course itself. Like whole course is about hash functions all the time. Okay, so we need to work with a non-ideal hash functions, and that is what we'll see next. So I will take a break now, and it's like 3:02. So let's meet at 3:10 in 8 minutes, and then we will see some how to make good hash functions. Okay. Okay. So now we will spend some time on limited independent and hashing, and at least I will teach you the first part of limited independence, because that is very important for the whole course. So randomized algorithms rely on independent random bits. Okay, but for us, I mean, there's a whole literature or whole questions. How do we get these random bits from the natural sources, from algorithmic sources? But that is not what we'll worry about. Okay. And pseudo-random net, we like to avoid or limit a number of random bits. So this is a very important and fundamental question in theoretical computer science, with lots of applications like hashing, cryptography, streaming, simulation, de-randomization, and a large topic in TCS with many connections to mathematics. So this is one area where there's a huge connection to mathematics. And what we will need in this course is like T-wise independent variables and hashing. So we will spend today and maybe the next lecture on T-wise independent variable and hashing. And that will complete our foundation on T-wise independent variable and hashing. And then I don't think we will ever have to come back to this. So once you should see these things, and after that you can say, oh, let's apply 3-wise independent, let's apply 4-wise independent, and then we will be done with it. Okay. Okay, so let me. Just one. Sorry, just changed my house. So still, I mean, people come with, okay, fix this, fix that. So, okay. So okay, so let's try to understand what is called T-wise independent random variable. Okay. So we all know random variables x1 to xn. So first let me define the independent random variable, which we saw already before, is that you have n random variables and they are going to take a range from B. So they are going to take values from B, like B is like some and they are all discrete. So B is like some B1. B consists of some B1, B2, Bn. Okay. Rather, so B is some range, and B say 1 to B. Okay. And when you call something independent, a probability that given any assignments of B1 to Bn from B, each of these guys take probability I equal to n, probability xi bi. So the way at least I like to view independent is that if I give you, say, n, if I give you, if I told you the value of x1 to xn minus 1, you still cannot tell me what the value of xn is. Okay. So like knowing some subset doesn't determine anything else. I mean, that is the most basic way to keep independence in head, according to me. Okay. And we say that a random variable is uniformly distributed in a range B. A probability that xi takes a value B is 1 over capital B. So like it takes any of these values with probability proportional to the size of the domain. Okay. So this is the independent random variable which we saw before. Okay. Now, let me first define the notion of what is called pairwise independent random variable or two-wise independent random variable, where, so for all I between J, I and J, and for all B, B prime in B, probability that xi takes B and xj takes B prime is product of individual probability, right? So I'm not saying, so look, when I say independent random variable, you like for any assignments of x1 to xn from the domain, from the range B, it's a product of the probability. But here I'm saying, look, I don't know about everything else, but if you give me two of them and whatever values the two of them take, their probability is a product of them. Okay. Okay. Now, okay. So if x1 to xn are independent, then they are pairwise independent, but converse is not necessarily true. Do you, I mean, we'll see this, but can you prove this? That if x1, x2, xn are independent, then they imply pairwise independent. Can we prove this? Anybody? Any idea? Have you seen this proof? Anybody has seen this proof? That if you have n independent random variables, then they are also pairwise independent random. For that matter, any subset independent random. Okay, so let's try. Okay. So this is why my course becomes much more slower. Okay. Our independent random variable implies pairwise or independent variables. Pairwise independent. Okay. So you just fix x1, x2, doesn't matter. Okay. Just for sake. So suppose x1, I want to show probability x1 takes A, and I think it's good to see this once. And x2, I want to show that this is probability x1 equal to A times probability x2 equal to B. This is what I want to show. But I can write this as summation, okay? Let's say B3 dot 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 Bn in B to the power n minus 3. So they all are over domain B, okay? And I can write this probability x1 equal to A and x2 equal to B and x3 equal to B3 xn equal to bn, right? This I can write because I'm summing over all bi's. Okay. But now I know that they are all independent. So this is summation b3 dot bn, right? What is this? Probability x1 equal to a times probability x2 equal to b product probability say xi I going to greater than equal to 3 equal to bi. Okay, this is what it is. Now these two are common, right? So I can take a b and summation b3 dot bn product this quantity, right? But what is this? What is product of? Can I say this is 1? Or did I make a mistake here in this proof? Okay, let's see. No, why did I take? I should just write. I don't need to write product here. Right? And you just take this. But now I'm summing this over all possible values of B3, Bn. So this quantity is going to be equal to 1. So probability x1 equal to a times probability x2 equal to b. Okay. I mean, there are many ways, but to show this. Okay. So this is one way to show, but what is more interesting is that if you have n by's independent, then actually it is independent for all subsets. Okay. So every subsets are independent. Like, I mean, if x1 to xn are independent, then any subset of the random variables are independent. But what about converse? If you can show that there are two-wise independent random variable, that does not imply that they are pair-wise independent random variable. Sorry, they are fully independent. For example, here is an example. So x1 and x2 are independent bits, like they are variable from 0, 1, 1. And what is my x3? So x3 is x1 XOR x2. Do you know what is x1 XOR x2? Is basically, let's see. So basically, it's exclusive OR. Okay. So it is exclusive OR. So okay, let's write it down. x1, x2, and x3, right? So exclusive OR basically means that it is 1, this function is 1, if and only if number of ones is odd. Okay? Odd. Okay? So for example, if x1 takes 0, 0, it will take 0, 0. It takes 0, 1, it will take 1. It will take 1, 0, then it will take 1, 1, 1, it will take 0, right? Or other way, I mean, if you you can also write it like summation xi mod 2. Okay. Now notice clearly x1, x2, x3 are, I mean, they cannot be independent. Why? Because the moment I know x1 and the x2, I also know what x3 is, right? So all three of them are not like, they're not all in. So what I mean by that, probability that x1 takes something A, x2 takes something B, x3 takes C, it cannot be 1/8. Okay, why? Because the moment I know what x1 is, what x2 is, x3 is completely determined by that. Okay, but are they pairwise independent? Okay, so for example, let's say, just to so maybe let me draw a picture here. Here your x1, x3, right? So here it is 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay. Now let's ask ourselves, and so these are like, so what is the probability that x3 is 0? Is basically either this case or this case. So half, 1/4 plus 1/4. So this is half. Okay. And what is the probability that x3 is 1 is, again, because what is the probability that x1 is 0 and x2 is 0 is 1/4, because they are uniformly at random over 0, 1. Okay. So this is half. Now let's ask ourselves, probability x1 is 0 and x3, x1 or x2, whatever it is equal to 0. What is this? So if they are really independent, then it should be 1/4. And why it is? Because look, the reason is, you fix x1, whatever the value you fix. Now whatever may be the value of x3 is completely determined by x2. Right? Now x2 takes either 0 and 1 with probability half, right? So this is 1/4. Or other ways, if you want to say that, look, 0, 0, x3 gets, x1 is 0 and x3 is 0 with probability 1/4, because each of this is 1/4, 1/4, 1/4, 1/4. Okay. So this is how, so what did we saw? We saw that while they are, I mean, you can try all other things, but look, so, but suppose if I told you, what is the probability that x1 is 0, x2 is 1, and x3 equal to 0? Can this happen? Is this happens? This is 0, right? But if they would have been independent, this should have been at least 1/8. So they are definitely not independent, right? I have exhibited you a value for which the product of probability is not same as the probability itself, right? So while these guys are two-wise independent, they are not fully independent. Okay. 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 So why are we like motivated in pairwise independent variable? So our main motivation is from streaming. Okay. So generally what you want is n uniformly distributed random variable x1 to xn, say bits, right? But can we store n bits? Look, we are in the regime where we need polylog bits or something of this nature. So keeping n coin tosses is impossible for us. Like head, tail, we cannot. Okay, we cannot keep these things. Okay, so we need to go away from fully independent object, okay, to something which is smaller. So what we are allowed actually is some storage of some order log n random bits, and where I between 1 to n, and we would like to generate these xi's in order log n time. So what happens is, so think of this way. So we will have, so think the best way to think is that we will have, say, y1, y log n coin tosses. Okay, so these are my purely random bits. Okay, now we will create some xi's which will be function of y1 to yn. Fi xi will be function of y1 to yn. So by using some log n random bits, or some log n random variables, we will create n random bits or n random variables, okay, where each range of each xi is 0 and 1. And more than that, we would like to generate this xi in order log n time. Otherwise, for the kind of purposes we are looking for, it is useless. If we want, and more importantly, we should be able to, we would like them to be pairwise independent and uniform over 0, 1. Okay. And finally, since we cannot store even all these n, we would like to generate them on fly. When I say, okay, look, now give me the xith random variable. Okay, so all you have stored basically will be y1, y2, y log n. Okay, now I will, whenever I need xi, I will compute this function f y1 to yi. And now notice this function f also, the description of this fi should be so simple or so easy that I don't even have to store that, because then that will also take a lot of space. So this is why these pairwise independent random variables are very, very important, is that you will have, so basically you have only pure ordered log n random bits, like pure source of random bits are like ordered log n, but you're able to generate much more random bits. They are not completely independent, but they are pairwise independent. And moreover, you can generate these xi's random variables whenever you wish, okay, and on the fly and in a small space. And this is what we will use for our purposes. So let me give you one such construction, and we will see more construction in the next lecture. Okay. Okay. So generating t-wise independent random variables, I will. Okay. So here is a nice construction. Okay, assume for simplicity that n is like 2 to the power k minus 1. Otherwise, we can consider the nearest power of 2. Okay. Okay. So hence, this k is like order log n. And now you have y1 to yk are independent bits. Okay. So think of this y1 to yk like pure coin tosses. Okay. Now, how are we defining this xs? For every s subset of 1 to k, I'm defining xs as summation, like what is xs? Is I in s, yi. So for example, so for each subset s in 1 to k, okay, you just look at those particular yi's and take this. So one way to do this will be, for example, say k equal to 5 or say 4. So n will be like 15. Okay. Now what will be x9? So x9 will be, so how will you write 9? 1, 0, 0, 1. Is it 9? Okay. So x9, I can write it as summation. This is basically y1 o plus y4, right? So for example, this, right? So with this k random bits, I have generated x1, x2, dot, 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 x15. 15 random variables, right? So if you had ordered log n random bits, or basically log n random bits, you will be able to generate n random variables. Now, they may not be fully independent, but what we can show that if S is not equal to T, then Xn and Xt are independent. But first of all, let's ask ourselves why Xs is uniform in 0 and 1. Okay. So recall, what did we say? Okay, S is not equal to phi. Okay, so the another way of writing Xs, so when Xs takes 1, Xs will take 1 if the number of Yi's that take 1 is odd and 0 otherwise. Okay, so suppose the size of S is like whatever size of S is S, which is greater than or equal to 1. Now, right, what are the possible values, right? What are the possible values Xs can take? 0 and 1. How many instantiation of Yi's are there for which it will take 0? It means for all even sized, for all even sets, like I choose which all guys from set S are going to take like 1. So if that is even, then clearly my Xs will take even. So this is like summation S choose Z, S choose I. Okay, so let's say this is 2 power S summation, or S choose 0 plus S choose 2 plus dot dot dot, right? All even terms. And we know what? This is 2 power S minus 1, which is 2 power S. So this is half. And similarly, when it will take odd, when it will take 1, when this is odd. So odd means S choose 1, S choose 3, dot dot dot, divided by 2 power S. Again, summation of odd coefficients is 2 power S minus 1, right? By 2 power S. So this is half. So clearly, all these random variables are uniform between 0 and 1, right? Now, why Xs and Xt are independent? Well, let's see if I have an extra page, and that will end our lecture there, hopefully. That's okay. So the simple idea is very simple. Look, for now, suppose this is S and this is T. For now, let's assume that T minus S is empty. Look, you could also have a case when T is like this and S is completely inside this. So, but, or other way around and this. Now notice, here are some things, some variables, which are still not fixed, right? Now, why, whatever may be the value this guy takes, okay? So let's ask ourselves, okay? So here, there's something like there is some T minus S. So what? So suppose you are interested in what is the probability that Xs takes 0 and Xt takes 1. For suppose this is what we are interested in. Okay, then I could have written this as probability probability Xs equal to 0 given that Xt equal to 1 times probability Xt equal to 1, right? This we can say. Okay, very nice. Now, what is the probability that xt equal to 1? Right? The probability, okay, maybe I did something not correct. Okay. No, this is not correct. This is not like, no, we have assumed that t minus s is phi. Okay. So let's do other way around. You will understand why this not, I mean, why this is not correct. Okay. I can also say probability that xt is 1 given that xs is equal to 0, because I'm assuming that t minus s is phi. Okay, times probability xs equal to 0. This is half. This we know. I just now showed to you that. Okay, but what is this? What is the probability that xt equal to 1 given that xs equal to 0? It depends. Now it depends on this part, right? And this we know is not equal to empty. Sorry, this is what I wanted to say. This is not equal to empty, right? So now, what is the probability that xt equal to 1? Well, number of odd sets here, right? Number of odd sets here. But I know that t minus s is not equal to phi, which implies t minus s is greater than or equal to 1, and number of odd sets here is same as, so suppose this quantity was c. So this is like 2 to the power t minus s, 2 to the power t minus s minus 1, which is half times half, which is 1/4. Right? So this just tells us that these set of random variables are independent, pairwise independent. Okay? So what did we saw? We saw a construction that you started with pure log n random variables, and with help of that you have created n independent random variables, right? And to do this, what do you need to store, right? What do you need to store? You just need to store some like log n coin bits, right? So you have log n coin bits, and I ask you, okay, so you have in the beginning itself of your process, you have done some n random coin tosses, and you have stored your log n bits of 0, 1. So you have stored a string of 0, 1 to the power log n. Okay, you have stored. Now, if I ask you, well, give me xs, right? Or give me the ith bit. Okay, or sorry, give me the ith random variable. So what will I do? Oh, this is I write down in binary, take down those bits, okay, take their OR and return you that. That's it, right? So this I can do on the fly, right? So this is one method of generating pairwise independent random variables. But here we had a limitation. What was the limitation? We only considered that 0, 1, like the range is 0, 1. And in the next lecture, we'll see how to generalize this to larger range and other kind of things. And we will use them to get a real algorithm to count distinct elements and for all other future purposes. Okay, so I think with this, I will stop my lecture. It's already quite long. Okay, so if you have any question, please ask. Hello, any question? Okay, if not, then let me thank all of you.